Continent of Africa splitting into two.
Africa is undergoing a dramatic transformation, a process so extraordinary that it's reshaping the continent itself. The Earth's crust beneath East Africa is breaking apart, tearing one of the largest landmasses on the planet into pieces. The Somali and Nubian tectonic plates are pulling away from each other, and a rift is expanding at an almost imperceptible rate, giving way to an ocean that would transform the world as we know it. In this narrative, we'll explore the details of this monumental event and consider whether humanity can adapt to such a profound geological change. In 2005, global attention was drawn to the seismic activity leading up to the Dabahu eruption, an extraordinary geological event. That September, the Dabahu area in Ethiopia's Afar Depression experienced over 130 recorded earthquakes in just 1 week. These quakes were powerful signals of an unfolding phenomenon, alarming local communities unprepared for such relentless intensity. As the tremors continued, tectonic plates beneath the region began pulling apart, with magma surging into the fissures. On September 26, the Dabahu volcano erupted, forcing approximately 6,300 people to flee their homes. The eruption left deep fissures, displaced families, and devastated livestock-dependent communities, revealing the vulnerability of those living in this tectonically active zone. Despite the immense human suffering, the Dabahu eruption offered an unprecedented scientific opportunity. Over 37 miles of fissures tore across the landscape, exposing molten rock and illustrating the rifting process in real time. This event showcased the divergence of the Somali and Nubian plates, with dramatic shifts in terrain observable within days. For geologists, it was a rare chance to witness plate tectonics at work on a human timescale. The Afar Depression emerged as a dynamic laboratory, demonstrating how tectonic forces create new landforms and potentially new seas, mirroring ancient processes like the breakup of Pangaea. The 2005 Dabahu eruption was not just a regional disaster but a vivid example of Earth's geological evolution. GPS and seismic data confirmed that the fissures marked the initial stages of an ocean-forming rift, providing critical insights into tectonic processes and their impacts. This event underscored the reality of Africa's rifting, with magma acting as a catalyst in the plate separation process. Researchers found in the Afar Depression a living model of the mechanics of plate tectonics, offering a glimpse into the eventual transformation of the African continent. The East African Rift, stretching 3,000 kilometers from Ethiopia to Mozambique, is one of Earth's most striking geological features. It exemplifies the immense forces shaping our planet and highlights the dynamic nature of landmasses. The Dabahu eruption was a turning point in understanding this rifting process, revealing its profound implications for Africa's geography and humanity's adaptation to these monumental changes in the millennia to come. This vast rift marks the boundary between two tectonic plates, the Somali plate, drifting southeast, and the Nubian plate, moving northwest. It isn't just a line on a map. The rift is a dynamic, evolving feature where the Earth's crust is actively breaking apart. The process began millions of years ago and continues to unfold before our eyes. Scientists often describe this zone as the most profound example of continental rifting on the planet. What makes the East African Rift particularly unique is that it's not just splitting the African continent in two, it's also creating entirely new geological structures, like valleys, fissures, and even future coastlines. Unlike the relatively slow tectonic shifts happening in many other parts of the world, this rift is active enough to be observed in human timeframes. The East African Rift owes its activity to one key driver: magma. Below the Earth's surface, magma wells up from the mantle, intruding into the rift and creating pressure that pushes the Somali and Nubian plates apart. As these plates drift away from one another, the crust in the rift zone becomes thinner and more fragile, forming fissures and fault lines. Magma intrusion is a core mechanism of this process, as molten rock finds its way into these fissures, cooling and hardening to form new crust. Over time, this creates a continuous cycle of destruction and renewal. Older crust is broken apart while new crust is added in its place. The East African Rift is, in effect, a conveyor belt for new land formation, a phenomenon more commonly seen at mid-ocean ridges under the sea. But the forces shaping the East African Rift extend beyond magma. Gravity also plays a key role. As the rift expands, massive sections of the Earth's crust sink under their own weight, forming dramatic escarpments and deep valleys. These valleys often fill with water, as seen in the region's iconic lakes like Lake Tanganyika and Lake Malawi, which trace the rift's trajectory. In total, this ongoing activity has already created one of the most geologically diverse landscapes on Earth, filled with volcanic activity, hot springs, and fertile soil. Over time, the forces pulling the Somali and Nubian plates apart will widen the rift to the point where water begins flooding the area, likely from the Red Sea and Indian Ocean. When this happens, Africa will split, and a new ocean basin will form between the eastern horn and the main body of the continent. This isn't mere speculation, it's an inevitability dictated by the principles of plate tectonics. Similar processes have happened before, most notably during the breakup of the supercontinent Pangaea. Around 180 million years ago, the Atlantic Ocean began to form when tectonic plates tore apart landmasses that would eventually become Africa and South America. Today's East African Rift is a smaller-scale version of that ancient process, but the end result will be no less dramatic. Though the creation of this ocean will take tens of millions of years, current activity shows we are witnessing its earliest stages. Some segments of the rift already dip below sea level, particularly in the Afar Depression, where magma-induced subsidence continues to lower the land. Satellite observations have shown that the rift is widening at an average rate of a few millimeters per year. Over geological timescales, this steady movement will result in the rift becoming unrecognizable from what it is today. When the ocean finally forms, it will not only change the physical geography of Africa but will also reshape the global map. Future generations may recognize a continent split into two distinct regions, with coastlines bracketing the newly formed ocean. The formation of a new ocean will dramatically alter the climate, ecosystems, and biodiversity of the region. Coastal areas will emerge where none previously existed, leading to new opportunities for marine habitats. However, this transformation will also pose significant challenges for human populations, particularly those reliant on the land for agriculture and livelihood. In places like the Afar Depression, where fertile valleys and lakes provide sustenance for communities, the flooding caused by ocean encroachment will likely displace thousands. Volcanic activity associated with the rift could also intensify, as magma continues to rise and erupt, potentially threatening nearby populations. Moreover, the changing geology may influence local climates by affecting wind patterns, rainfall distribution, and access to freshwater resources. The East African Rift serves as a vivid example of tectonic forces reshaping our world. Yet, the ongoing changes in this region are part of a larger, more intricate geological narrative, one that hinges on the unique characteristics of the Afar Depression, the epicenter of rifting activity. At the heart of the East African Rift's dramatic transformation is the slow but relentless movement of Earth's tectonic plates. The Nubian Plate, which makes up most of the African continent, and the Somali Plate, representing its southeastern portion, are pulling away from each other at a rate of up to 2 inches per year. Though seemingly negligible on human timescales, this divergence accumulates over millions of years, resulting in massive structural changes to the Earth's crust. This movement is driven by convection currents deep within the mantle, where heat from Earth's core creates circulating currents of molten rock. These currents generate enough force to fracture the overlying crust, creating a divergent boundary between the Nubian and Somali plates. Unlike convergent boundaries, where plates collide and create mountains, divergent boundaries like this one are zones of separation, tearing the surface apart to create new landscapes. The East African Rift is essentially a nascent version of what occurs along the world's mid-ocean ridges, like the Mid-Atlantic Ridge. Here, as the plates diverge, magma wells up from the mantle to fill the void. As it cools, this magma solidifies to form new crust. Over time, this cyclical process will expand the rift, eventually creating a full-fledged ocean basin. The mechanism is both simple and profound. As magma pushes upward, it weakens the lithosphere, causing it to fracture and thin. These fractures develop into fault lines and fissures, creating steep valleys and escarpments. In the East African Rift, the process is evident in regions like the Afar Depression, where active magma upwelling creates visible geological features, from basaltic plateaus to volcanic cones. This phenomenon of crustal creation is not unique to modern times. Around 180 million years ago, a similar divergent boundary formed between what are now the South American and African continents, leading to the formation of the Atlantic Ocean. The East African Rift offers a rare chance to observe this immense process occurring on land rather than beneath the ocean. The rift's progression is far from quiet. Seismic and volcanic activities are constant reminders of the forces at work beneath the surface. The tectonic stress generated by the diverging plates leads to frequent earthquakes, many of which are strong enough to alter the region's topography. For example, in the 2005 Dabahu event, over 130 earthquakes struck within a week, providing a striking example of how these forces interact on a rapid timescale. Volcanic activity is equally significant. The East African Rift hosts some of the world's most active volcanoes, including Erta Ale in Ethiopia and Oel Doinyo Langai in Tanzania. These eruptions not only release vast amounts of magma but also reshape the surrounding landscape by depositing new layers of volcanic rock. Magma chambers beneath these volcanoes also play a critical role in weakening the crust, accelerating the rifting process. Another hallmark of the region is the formation of geothermal features, like hot springs and fumaroles, where heated groundwater escapes to the surface. These features signify the proximity of magma to the Earth's crust. Over time, the combined effects of plate divergence, magma upwelling, and seismic activity will lead to the formation of a new ocean basin. As the Somali Plate continues to drift away from the Nubian Plate, the rift will expand and eventually allow seawater from the Red Sea and the Indian Ocean to flood the region. Once the process is complete, the rift will resemble modern-day tectonic boundaries like the Red Sea or the Gulf of California. The Afar Depression, a low-lying area near the rift's northern end, offers a glimpse into this future. Parts of the depression already sit below sea level, and cracks in the crust occasionally allow groundwater and magma to interact, creating boiling mud lakes and temporary lava lakes. Eventually, these features will give way to permanent water bodies, marking the birth of a new ocean. The geological processes driving the East African rift are interconnected in profound ways. Plate divergence sets the stage, but it's magma upwelling, seismic activity, and the resulting crustal deformation that turn this rift into an active zone of change. The rift serves as a powerful demonstration of the delicate interplay between tectonic forces and surface processes, creating both challenges and opportunities for the region's ecosystems and communities. Understanding the geological mechanics of the East African rift helps us appreciate the sheer scale of change underway. But these natural forces aren't operating in isolation. Their effects ripple into the lives of the people who call the rift region home, which leads us into the next problem. How will communities adapt to an environment constantly being reshaped by the Earth's restless energy, and how will all of this actually happen? The thing is, it's not going to happen all at once. The formation of a new ocean in the East African rift is a step-by-step process that transforms landlocked terrain into a vast body of water. This transformation is governed by tectonic forces driving the Somali Plate and Nubian Plate apart. The progression unfolds in three distinct stages. First, we'll see it go from rift to valley. This stage begins with the formation of fault lines and fissures as tectonic plates diverge. Magma wells up through the thinning crust, creating volcanic activity and earthquakes that reshape the landscape. Over time, these processes widen and deepen the rift valley, forming elongated depressions bounded by steep cliffs. Then, there's the valley to the Gulf. As the rift deepens, parts of it may dip below sea level. Water from adjacent oceans or seas, like the Red Sea or Indian Ocean, begins to seep in, forming isolated gulfs or narrow waterways. This stage is exemplified by regions in the Afar Depression, which are already below sea level and demonstrate early signs of water intrusion. Eventually, we see it go from gulf to ocean basin. Over millions of years, continued divergence widens the gulf into an expansive ocean basin. Magma continuously rises to form new seafloor, and tectonic activity keeps the boundary active, further expanding the ocean. At this point, the rift's geology will resemble that of established mid-ocean ridges, and from there, it would slowly become a full ocean. But when will all of this take place? The East African rift provides a rare chance to witness the early stages of oceanic creation. While the process seems almost frozen on human timescales, scientists estimate that a fully formed ocean will emerge in roughly 5 to 10 million years. Current rifting rates, approximately 2 inches per year, drive this timeline, though geological disruptions could accelerate or delay the progression. Comparatively, the Atlantic Ocean took tens of millions of years to develop after Pangaea split apart. The East African rift is following a similar blueprint. As the rift progresses into an ocean, the separation of the Somali Plate from the African continent will create a striking geographical shift. A new island, comprising parts of Ethiopia, Somalia, and Djibouti, will form along the rift's eastern boundary. This landmass will be surrounded by the waters of the newly formed ocean, much like Madagascar split from Africa millions of years ago. The shoreline of the remaining continent will undergo dramatic alterations as well. Countries like Kenya, Tanzania, and Ethiopia may see their coastlines redefined by this new body of water, while regional ecosystems adapt to the influx of oceanic conditions. Over time, this new geography will shape human settlement patterns, biodiversity, and resource distribution, cementing its place as a key factor in Earth's evolutionary narrative. While the rift's transformation into a new ocean is still in its infancy, the groundwork is being laid for a profound geological and environmental shift, a process that has happened repeatedly throughout Earth's history. Understanding the East African rift's future requires examining past geological events that mirror its development. These historical processes reveal the intricate link between tectonic activity and global change. Roughly 30 million years ago, the Arabian Plate began separating from the African Plate, creating a rift zone that would evolve into the Red Sea. Initially marked by volcanic activity and seismic events similar to those in East Africa, the rift gradually widened as magma upwelled, forming new oceanic crust. Today, the Red Sea exemplifies a mature rift transitioning into an ocean basin, mirroring the expected future of East Africa. About 200 million years ago, the supercontinent Pangaea began to break apart, driven by diverging tectonic plates. The fissures widened into rift valleys, eventually giving birth to the Atlantic Ocean. This ancient process demonstrates the potential for East Africa to one day host a similarly vast ocean, reshaping the continent and global geography. Both the Red Sea and the Atlantic Ocean are familiar features today, but their formation was a gradual and transformative process. They serve as reminders of how slowly but significantly Earth's surface evolves over millions of years, shaping the world we now take for granted. Major geological transformations often lead to profound ecological consequences. When continents drift apart or rifts evolve into oceans, ecosystems are reshaped, and biodiversity often flourishes. As land fragments, isolated ecosystems form, allowing species to evolve independently. This isolation spurs biodiversity, as seen in Madagascar's unique flora and fauna that emerged after its separation from mainland Africa. The influx of seawater into rift zones creates unique habitats, fostering marine ecosystems ranging from shallow-water coral reefs to deep-sea trenches. These ecosystems nurture species uniquely adapted to their environments. As climatic conditions shift with the formation of rift valleys and oceans, coastal zones experience new weather patterns, impacting flora, fauna, and human activity. The East African rift holds similar potential to drive biodiversity as ecosystems adapt to its gradual transformation. Geological events like rifting also have far-reaching impacts on climate systems. The formation of a new ocean in East Africa could mirror changes observed in previous epochs. About 2.8 million years ago, the rise of the Isthmus of Panama altered ocean currents, cutting off direct flow between the Atlantic and Pacific Oceans. This event significantly influenced global climate, creating conditions for ice ages in the northern hemisphere. As East Africa's new ocean develops, shifting sea and wind currents may similarly alter the region's climate. Coastal zones could experience cooler, wetter climates, while inland regions might face aridification, reshaping agricultural patterns and ecosystems over time. Geological history demonstrates that processes like those underway in East Africa have reshaped the planet, driven biodiversity, and transformed climate systems. By studying events like the formation of the Red Sea and Atlantic Ocean, scientists can better understand what lies ahead for this emerging ocean and the region it will forever change. Modern technology plays a critical role in understanding and monitoring the East African rift's progression. By combining satellite observations, seismic instruments, and advanced models, scientists can not only track current changes but also project the rift's long-term transformation. The rift's evolution has been meticulously tracked through cutting-edge satellite imaging and GPS technology, enabling real-time monitoring of ground deformation and tectonic shifts. For example, satellite interferometry compares radar images over time to identify subtle ground movements. In the East African rift, INSAR has detected areas of ground subsidence, uplift, and fissuring associated with magma movement and tectonic activity. Fixed GPS stations across East Africa measure tectonic plate divergence, detecting movements as small as a few millimeters and confirming the Somali and Nubian plate steady separation at rates of up to 2 inches per year. Satellites have captured images of magma rising beneath the rift, contributing to surface deformation and seismic activity. By analyzing thermal imaging and ground changes, scientists can pinpoint regions where new crust is being created, particularly around active volcanic areas like Erta Ale. Seismic networks deployed across the rift region provide invaluable data on subterranean activity. Arrays of seismometers identify the frequency, location, and magnitude of earthquakes along the rift, with clusters of low-magnitude tremors often signaling magma movement, while larger quakes indicate significant tectonic shifts. Depth profiling through seismic wave analysis reveals the depth of magma chambers and fault zones, showing that volcanic systems within the rift are fed by magma intrusions extending several miles below the surface. These advancements allow for a detailed understanding of the rift's progression, offering insights into a phenomenon that could redefine the region and its ecosystems for millennia to come. These seismic insights not only help forecast eruptions but also contribute to understanding the complex interplay between tectonic forces and volcanic activity. Predicting the future landscape of the East African Rift relies on advanced geological models that incorporate real-time data, such as dynamic simulations of rift expansion. These models simulate the continuous divergence of tectonic plates, predicting the eventual formation of a new ocean basin. This includes mapping the timeline for the rift's transition from a continental valley to a fully submerged ocean. Projections show how areas like the Afar Triangle may eventually form an island, separated from the African mainland by seawater. By integrating data from ground deformation and seismic studies, scientists model the interactions between magma and crustal structures, offering predictions on where new volcanic systems may emerge or how crustal thinning will advance. Innovations in remote sensing, AI-driven data analysis, and autonomous field instruments are expanding the scope of rift monitoring. AI algorithms analyze seismic and satellite data with speed and accuracy, identifying patterns that human observers might miss. Drones and rovers can navigate dangerous terrains to capture high-resolution images and collect ground samples, providing critical data from the rift's most inaccessible zones. As technology evolves, so too does our ability to monitor and predict the East African rift's changes. These tools have not only provided detailed insights into the rift's current state but also set the stage for anticipating its future. With these advancements, humanity is better equipped to understand what's coming and prepare for it. The people living in the immediate vicinity of the East African Rift, particularly in the Afar region, have developed remarkable strategies to adapt to ongoing geological changes. These communities have endured some of the planet's most active tectonic regions, shaping their ways of life around intense volcanic and seismic activity. Due to scarce freshwater resources, locals have cleverly utilized geothermal energy. In the Afar Depression, volcanic steam vents provide a constant heat source. Indigenous communities collect steam rising from these vents and condense it into drinkable water, creating simple yet effective systems for water purification and collection. This practice allows the Afar people to survive in an otherwise arid environment, transforming what might be seen as a hazard into a vital resource. Another remarkable survival technique involves the use of obsidian, a volcanic glass widely available in the region. The Afar people have a unique method for testing obsidian to ensure it is not contaminated by harmful volcanic gases. Before using obsidian to craft tools and weapons, they test the mineral against natural benchmarks to confirm its safety and effectiveness. This traditional practice is crucial in a region where volcanic eruptions are frequent. While living near active volcanoes and seismic zones presents significant risks, the rich mineral resources of the region provide substantial economic opportunities. The East African Rift is home to valuable resources, including geothermal energy, volcanic ash, and minerals like gold, copper, and salt. Geothermal fields in Ethiopia are already being tapped to harness the rift's underground heat, contributing to a growing clean energy industry. As geothermal power plants expand, they could provide renewable energy locally and on a broader scale, offering a model for sustainable energy production worldwide. The fertile volcanic soils of the region also attract farmers, both local and international, seeking to capitalize on the unique ecological advantages for agriculture. As the East African Rift slowly transforms into an ocean, it is expected to dramatically reshape the environmental landscape. The formation of a new ocean could influence global ecosystems by altering atmospheric circulation patterns, potentially leading to changes in rainfall and weather across the continent. Arid or semi-arid areas might receive more moisture as ocean currents redistribute water, enhancing agricultural potential and biodiversity. Conversely, regions that already experience substantial rainfall may face drier conditions, particularly inland. The creation of a vast body of water could lead to a significant redistribution of heat and moisture, triggering widespread changes in regional and global climates. These shifts may create new environmental niches, prompting species to adapt, migrate, or face extinction. While such transformations are monumental, they are a testament to Earth's resilience and capacity for change. What do you think? If you enjoyed this video, don't forget to subscribe to our channel. See you in the next one.